Attention all passengers, this is the screencast for Section 6.1, Example 8. Our flight plan was to leave San Francisco International Airport, headed due east. However, there's a 65-mile-an-hour wind with a bearing of 60 degrees. We're going to find the compass heading that we should follow and determine our ground speed. And get to our destination on time. Thank you, and have a nice flight.
Alright, co-pilots, our destination is to go due east. However, we've got this wind that's blowing us a little farther north than we would like to go. So I've got a drawing of the two vectors. This is the vector that we need to have our compass headed at in order for us to fly due east. So our gauges are going to read one thing, but we're actually going to be flying due east. We just need to figure out what our gauges have to read in order to get us to our destination. Well, I'm going to move the wind vector to the head of our vector. That will create an equivalent vector that I can add to our compass heading vector. So when I add the two together, it should make our flight due east. I'm going to call P our compass heading vector, W our wind vector, and V our flight plan vector, and that one's the due east vector. Our due east vector, I don't know what its x-coordinate is going to be. I don't know what our ground speed is going to be yet. We'll find that out later. But I do know that the y-coordinate has to be 0. We do not want to fly any north or south. We want to fly straight east. Well, since our due east vector is going to be a sum of our plane's compass heading vector and the wind vector, I can add those together. Our plane is flying 450 miles an hour without wind speed, so that's going to be our magnitude of our compass heading vector. And I don't know theta yet. The magnitude of our wind speed is 65 miles an hour. Theta is going to be the angle of the vector off of the positive x-axis, so 30 degrees. So now I can set up an equation using all of the y-coordinates of these vectors to solve for theta. I got that theta is negative 4.14 degrees, but theta is a measurement from straight east. Navigation is a measurement clockwise from north. So I actually want a compass heading of 90 plus the absolute value of theta in this case. So we should set our compasses for 94.14 degrees. Now we also have to find out how fast we're going to fly because that wind is going to add speed as it's blowing us also not just a little bit north but also a little bit east in the direction that we're going. So we're probably going to get there faster than we wanted to. We need to make sure that we got a runway available. So our flight vector is going to be the x-coordinate of our plane vector plus the x-coordinate of our wind vector, comma 0. Again, not going north or south, we're just going east according to our plane, our original flight plan, and the wind vector. So my ground speed is going to be the magnitude of this vector, which I get to be 505.12 miles per hour. If our compasses read that we're going 450 miles per hour at a direction of 94.14 degrees, and the wind is blowing us at an angle of 60 degrees at 65 miles per hour, we are actually going to be headed due east at a speed of 505.12 miles per hour. I'll let ground control know and make sure there's an open runway because we're going to get there early.
Attention passengers, we'll be arriving at our destination a little bit early today. I hope you enjoy your extra time and have a great stay.
So now try problem number 43. An airplane is flying on a compass heading of 340 degrees and 325 miles an hour. So we know what the compasses say. And a wind is blowing at the bearing of 320 degrees at 40 miles an hour. We're supposed to find the component form of the velocity of the airplane, so what the airplane is actually flying. Then we'll find the actual ground speed using that vector. My first step will be to draw a picture so I can get a better understanding of what is going on visually. I know the airplane is flying on a path of 340 degrees, which would be clockwise from north, which means then that it is 20 degrees short of going all the way around to 360 degrees, so that means it would be 110 as our theta. The wind is headed at 320 degrees, which would be 40 degrees short of 360, so we need 90 plus 40, so that would be a theta of 130 degrees. So if I take the wind vector and put it at the head of the compass vector, I should be able to get the plane's actual path, which would be vector v. So v, our actual flight vector, is going to equal the vector for what our compasses read plus the vector of the wind. Our compasses are reading 325 miles an hour, and we said theta was 110 degrees. And the wind is traveling at 40 miles an hour, heading at a theta of 130 degrees. So after adding the x-coordinates and the y-coordinates together for our compass vector and the wind vector, I get that our actual flight vector is negative 136.87, 336.04, which means that every hour the plane is flying 136.87 miles west and 336.04 miles north. Part B asks us to find the actual ground speed, which is the magnitude, and the direction of the plane, which we can find solving for theta. First, I'm going to find the magnitude of the vector to get the ground speed. And I get that the plane is actually traveling 362.84 miles per hour. So in other words, the wind is pushing it a little bit faster than the actual gauges are reading. Now, in example 6, we found the direction of our vector by using the x-coordinate and cosine theta expression, or the y-coordinate and the magnitude times the sine of theta expression to solve for theta. This time I have both coordinates, so I could use inverse tangent if I wanted to. So the tangent of my reference angle in quadrant 2, theta, is going to be the opposite, so the vertical coordinate 336.04 over the horizontal coordinate negative 136.87. So if I find the inverse tangent in my calculator, I get negative 67.84 degrees. However, that would land me in quadrant 4. I need to get that same reference angle in quadrant 2, so I'm going to take 180 degrees and subtract 67.84 as a reference angle to find out what theta that would be to get me in quadrant 2. So now I've got theta, which is a measurement from the positive x-axis to my vector, but I need a measure of navigation, which is clockwise from north. So I'm going to take 112.16 degrees and subtract 90, and then take that away from 360 to find out clockwise from north what my angle is. And I get that my navigational heading would be 337.84 degrees, which is definitely in quadrant 2. So I can see the effects that this wind had on what my compass headings are for my airplane. I mean, my plane reads that I'm going 340 degrees, the wind is blowing at 320 degrees, my actual direction, navigational direction, is 337.84 degrees, which is kind of in the middle, but not directly in the middle, because my flight was 325 miles an hour, my plane, and the wind is only blowing at 40 miles an hour. So it's not going to have an equal effect against me as my own flight path is. So it's going to be closer to what my gauges read than what the actual wind direction is. I also see that my plane was flying at 325 miles an hour without the wind, and then the wind is blowing another 40 miles an hour, which doesn't make 360 miles an hour because the wind isn't blowing the exact same direction as the plane is headed. It's blowing a little bit off the path, so it's only going to bump my speed up to 362.84 miles an hour. Still a pretty good bump though.